Hello, ladies. So I guess exciting first lesson. I guess our first flipped classroom video for chapter 5. This is exciting. So let me know how it goes at the either at the end of the lesson or maybe I don't know if you want to within the week, just to see how this is going and if this is something that you would like to continue doing. So just as a quick note here, I'm not going to explain this for every single chapter. I trust that you guys can read a front page. But so just for now, just see what kind of my little work does. So here I just want to kind of explain. So here, this basically front page just looks at it's a tentative overview of what we're going to be doing. And it's tentative, so it's not set in stone. So if there's any issues, problems, if we need to redo something, if you have any questions, or even just to let you know what's coming up, this will give you a little rough outline of how this unit's going to go. So, and just as a quick note, Wednesday we're going to have our 5.1 and 5.2 quiz. It's just going to be a little itty bitty small quiz. Should be about half an hour, so there should be some time to do some practice questions or create a little mini cheat sheet for that. So it'll just be a nice little small one, so nothing to really worry too much about. And here we also have our key terms. These are just ones that these are just words that you'll see throughout the chapter. I don't ask you to memorize these definitions. They're just important to know, so I just kind of put them out there for you to see if to help you study. Alright, so that's that. So let's get into section 5.1. So we just talked about basically all the trig functions and how it relates to your unit circle. So now what we're going to be doing is we're going to be graphing these functions. And we'll only be looking at the sine and cosine. We'll be looking at tangent in section 5.3, but it's kind of unrelated in a way when we're looking at the graph. So that's kind of why it's in its own little section. So today we're just going to be looking at sine and cosine. And just as a note, these fill in the blanks, I don't have my Smart Ink. It's not working for whatever reason, so I'm just going to be typing them into the Word document, and I'll just highlight them in like a different color so that way they kind of stand out for you ladies. And at any point, if you need to pause, definitely go for it. You can work at this at your own pace, although try not to take 10 years to write down one word. Try and go along as I'm talking about it and typing it in. But you're more than welcome, obviously, to pause the video whenever you need to and do anything that would help you guys out. Alright, so to start, so we're going to be looking at sine and cosine functions, and these are what we call periodic functions. Right, so this means that they are a function that repeats itself over regular intervals or cycles of its domain. And these ones, these kind of cycles or intervals that we're going to be looking at are what we call periods. Or this is just one cycle, one interval. And there is an equation to find out like how long or how big a period is for your graph. And I'm just going to quickly write out, we have a generalized form of our sine and cosine function. So I'm going to quickly write that out here. So we have y is equal to some constant a times the sine of some constant b multiplied by x. And we also have y is equal to some constant a multiplied by the cosine of some constant b and x. So those are just the general forms. Later on we will be getting into, we will be adding on to it a little bit, but it's typically, just for now, this is what we'll be dealing with. So the equation to find out how big your period is, math-related period. So we're going to be looking at 2 pi is divided by the absolute value of b. So we have 2 pi is divided by the absolute value of b. When we're dealing with, so this would obviously be in radians. If we were to deal with degrees, it would obviously be, instead of 2 pi, it's going to be 360 degrees. So just the equivalent of what your degrees and radians values would be. Alright, so now we're going to go on to, I guess we can give a name for all these curves. And it's kind of a crazy word. It's called sinusoidal curves. And if you can kind of take a guess, it has to do with, it's going to be basically, it's going to curve that will look like the sine graph. So if we look over in this little example here, so if you were to look at the graph of sine, it starts off in the origin and it kind of follows a nice little wave. So if it has that little wave that fluctuates back and forth, and what could look like sine, then it's definitely a sinusoidal curve. So there's also that example of, if we look below in this picture, we have that, it could be periodic, but that one is not sinusoidal because this one does not follow the motions of what a sine graph would do. So here, yes, this little bump here goes great, it's going up, but then it repeats that pattern. So it would need to fall down into a sort of wave-like pattern in order for it to be sinusoidal. So this example here is periodic but not sinusoidal. All right, moving on. So when we're graphing sine and cosine, this is assuming that they're in standard position. These are going to be related to the points on the unit circle. So below here we have our sine and cosine graphs along with their unit circles, and they're all related to the point P on the unit circle. So specifically for the graph of y is equal to sine of theta, your y value is going to be related to that y coordinate on your point P on the unit circle. So let's look at, say for example, pi over 2. We can follow this little dotted line here. So here you'll notice that y is going to be at 1 and your x is at pi over 2. When you're looking at your unit circle, you'd have that coordinate for pi over 2 is at 0 and 1. And so if you notice that sine value, which is that y coordinate there, that is the exact same of what our graph here looks like. So your y value is going to be at 1. Another example if you want to. This point value here, we're looking at pi over 4. If you were to look at that sine coordinate on your unit circle, I believe it's root 2 over 2, which is approximately where this little guy here is. Okay. And so similarly, if you guys could take a guess, for cosine, instead of looking at that y coordinate on your point P, we're going to be looking at that x coordinate. So if you remember, I told you about the unit circle that your coordinates, it'll be your x coordinate will be your cosine theta, and your y value will be the sine theta. So that's exactly what this is doing here. So when we're looking at pi over 2, when you're looking at pi over 2, you have your coordinate P will be 0 and 1, and that's exactly where it is. That x value, cosine, will be at 0. So that will be your y value there. All right. So there's some nice relationships there. We're going to keep on going here. So the coordinates of point P repeat after point P travels completely around the unit circle. The unit circle has a circumference of 2 pi, which means that the period of sine theta and y is equal to cos theta, they will each be 2 pi. So yeah, basically we'll start at the beginning of our unit circle, and our graph is going to be going through each and every single one of those points until it returns back to that original starting point, which is, and if you compare that with the graph, that's exactly what's happening. We go from 1 to all the way to 0, down to -1 to 0, and then back up to 1. So that's exactly what's happening here. So we're going from 1 to 0 to -1 to 0, and then back to our starting position of y is equal to 1. So kind of a nice little relationship there, just to continue on there. Alright, so moving on down. Just one quick note about sinusoidal functions. Here we're going to talk about the amplitude. So the amplitude is the maximum vertical distance the graph of a sinusoidal function varies above and below the horizontal central axis of the curve. So in other words, the vertical distance from the x-axis to the maximum or minimum values. And one quick note is that this, in other words here, when we're talking about the distance from the x-axis, this only works when your sine or cosine are in standard position. So looking down here, the horizontal central axis, or in this case, because sine is in standard position, it's that little line there that would cut your, that would horizontally cut your graph in half. And you're looking at that distance from this line here up to your maximum or to your minimum. And just remember, it's a distance, so it's always going to be positive. And there is actually, very nicely, there is an equation that we can use for this. So, and I'm going to write this in absolute value brackets just so that we remember that it's going to be your positive value. So we have our amplitude is equal to your maximum value minus your minimum value, and that's all going to be divided by 2. So it's kind of All right, so moving on down. So let's just look at, we're gonna look at a couple, I think 3 examples here, and then I'll cut you loose for assignments. So here we're just gonna consider the graph of y is equal to sine of theta, and I forgot to change this here, and I changed this on your notes, but it should be the sine of theta for the domain of 0 to 2 pi. So here we have the table of values. This one's just kind of sideways, but it gives it in radians and degrees. Obviously, we're just going to be dealing with radians for this example because our domain here is set for 2 pi, which is obviously our radians value there. So let's talk about some of the characteristics looking at the graph of sine of theta. Here we can say that the graph is periodic. If we were to extend that, it would follow, or it would go in that repeating pattern. So we would, in theory, call this periodic if we were to keep on graphing this. We can also here say that the graph is continuous, and basically continuous, if you remember what that means, basically we can connect every single dot. So we're not going to be using, or we will be using values in between pi over 6 and pi over 3. It's all very legit, so we can totally use it. So we'd be connecting our points all the way throughout this graph, which means that it's continuous. Here we can say that the domain, they're obviously, if we want to go with a general graph of y is equal to sine of theta, we would say that its value, or that theta would be an element of all real numbers. If you were just looking at this example, it's clearly only from 0 to 2 pi, but let's do a general case here. So we can say here that the domain, I'm just going to get here, so the domain is that theta is an element of all real numbers. And I'm just going to denote this as an R, but definitely go ahead and use it as your double, or your like a double bar R, I think is kind of how Miss Windrum showed you. So draw it as you know how, but I'm here going to denote it as just R. Okay. So our range is at, if you're looking at these values here in the graph, your highest point is 1, your lowest point is -1, so we can say that -1 is less than or equal to y, which is less than or equal to +1, and that is that y is an element of all real numbers. So basically just repeating, we should already know what this means, but just to say it again, so the range is talking about your y values, so it can go anywhere between 1 and -1, but not outside those values. So there in itself, we already talked about the maximum and minimum values. So your maximum is obviously going to be 1, and your minimum is going to be -1. And the amplitude of the curve, this one here is, there's been no changes to the sine of theta, so if you really just wanted to just jump to it, you could say that the amplitude is 1. If you wanted to use your amplitude equation, it's your maximum value minus your min, so you'd have 1 subtracted by -1. And that is all going to be divided by 2. And if you solve that out, you should get 2 over 2, which is simply equal to just 1. So that kind of helps reinforce that we already know that it's, or I guess what we've already talked about. Here, so your period is just 2 pi. Just remember, so your period is 2 pi over the absolute value of b. Here in this case, b is equal to 1, so it would just be 2 pi over 1, which is just 2 pi. Okay, and the last one, so our y-intercepts, we have here that x is equal to 0, and it's the only value there, so you can say x is either equal to 0, or you could just put 0, 0 to denote our origin. So cool stuff.